One. Hello and welcome to the Everything Else Show. I'm Martin Willis, your host. We have a great guest. I had the chance to meet Dr. Jeffrey Bennett down in North Carolina several years ago, and I'm real excited to have him on the show. We're going to be talking about relativity, a little bit about space, black holes. It should be a real fun show. So Dr. Jeffrey Bennett, he holds a BA in biophysics from the University of California at San Diego, and an MS and PhD in astrophysics from the University of Colorado at Boulder. He specializes in mathematics and science education, writing and speaking for audiences. Actually, he was on a tour. We're going to talk about that, talking about relativity. Went to cities all over the country. Great guy. Glad to have him on. How are you, Jeffrey? Welcome to the show.
Great, and thank you very much for having me on today.
Yes, it's always a pleasure. I have listened to your shows talking about relativity, or one of them, I should say. I found it fascinating. And so, how did that all begin? You were basically, they were reaching out and asking scientists to talk about this, to celebrate 100 years.
Well, yeah, 2015 was the 100th anniversary of Einstein's publication of his general theory of relativity. And so for that, the United Nations had declared it the International Year of Light. And so they were looking for people to go out and help the public understand relativity. I'd already written a book on relativity. So I thought, well, I'll just email friends and say, if you want to have me come give a talk at your university or wherever, I'll do it. And I ended up in 25 different cities, mostly on college campuses, but a few other places, science museums and things like that. And it was a lot of fun.
Great. And also, I know you are doing some talks on climate change, and I would actually like to, I'll talk to you about that at a later time. I'd love to have you back on that. If you feel up to doing it sometime, we can talk about that later.
Absolutely. And I should say, in fact, that the way that happened was after 2015 ended and it wasn't the 100th anniversary of relativity anymore. I thought, oh, what am I going to do now? And I decided I should pick a different topic and go on tour for that. So that's what I'm doing now with global warming.
I see. Great. So something happened in astronomy today. Let's talk about that. Two stars colliding.
Yeah, so this is a really pretty big deal, and it is relativity, so it's right up our alley here for perfect timing for having me on tonight. If we had done it a month ago, we wouldn't have had this new thing to talk about. So you probably heard a couple of years ago, in the end of 2015, the LIGO Observatory, stands for Laser Interferometric Gravitational Observatory. The LIGO Observatory came online in its new advanced way, and it had been built specifically to detect these things called gravitational waves that are important prediction of Einstein's general theory of relativity. Now, I should mention, we actually knew that these things existed already, not just because Einstein had predicted them, but because we had very strong indirect evidence that they exist. And the way that came about is you have places in the universe where you have two very, very compact, massive stellar corpses, like two neutron stars or two black holes, and they're orbiting around each other. Hopefully viewers can see what I'm showing here. And the idea is that, according to general relativity, when you have two fast-moving objects orbiting like this, they should be emitting energy in the form of gravitational waves out into the universe. And that energy that's being carried away, since that means the system is losing energy, that orbit is going to gradually decay, get smaller and smaller, and eventually you would expect those objects to merge. So starting in the 70s, astronomers had detected some of these binary pulsars like this, two neutron stars orbiting each other, and their orbit was indeed decaying exactly the way it should if it was decaying because of the emission of gravitational waves. So we knew the gravitational waves really were being emitted, causing this decay, but we couldn't detect them directly. And what LIGO has done is it's actually detected the gravitational waves themselves coming from the last moment when the two objects merge into each other. So the first discovery was in 2015, and there have been a total of 4 of these, and those first 4 all involve 2 black holes crashing into each other. And from Einstein's equations and from the signal you get, you can actually calculate exactly how massive each of the 2 black holes were, how far away they are, and so on. But because they were black holes, and I know you want to talk more about black holes, but black holes don't emit any light. And therefore, when they crash into each other, they still don't emit any light. They emit lots of these gravitational waves, and that's how we got the signal. But you couldn't point a telescope there and say, oh, there it is in visible light, for example. Wow. Today's announcement is about 2 neutron stars that collided with each other, merged together. And because those are physical objects, right? They're the remains of what were once big, massive stars that are now just balls of neutrons. When they crash into each other, it's a real collision. And so there's all kinds of light emitted in addition to the gravitational waves. So what happened this time was LIGO recorded the signal in gravitational waves, but astronomers also saw it in virtually every wavelength of light that there is. You can point up in the sky and see, there it is in visible light, there it is in X-rays, there it is in radio, and we also have the gravitational wave signal.
Now, how many light years away did this occur? In other words, how long ago did this happen?
I believe this one, if I remember, don't quote me on this, but I believe they had said this one was about 130 million light years away. So this is happening in a distant galaxy, but 130 million light years is actually, in universe speak, not that far. But
now, the 2 neutron stars, were they part of a binary system of a solar system, do you think?
So presumably, what happens is to form a neutron star forms in a supernova explosion. So these are these giant explosions that can occur at the end of a massive star's life. So the only kinds of stars that undergo supernovae are massive stars, at least 8 times the mass of the sun or more. Stars like the sun, they die in a much gentler fashion and leave behind corpses that we call white dwarfs. So a neutron star would have formed when a massive star exploded. So presumably what you had here sometime in the distant past was 2 massive stars orbiting each other, and one of them exploded and became a neutron star, and then sometime later the other one exploded and became a neutron star, and then you have these 2 neutron stars orbiting around each other.
I see.
And they can get very close because what you have here, a neutron star's mass is typically about 1.5 to 2 times that of the sun. It's the remains of a much more massive star that blew out a lot of its mass into space. But what it has, the reason it's called a neutron star is during the supernova and the collapse in the center that drives that mass, more than the mass of the entire sun, gets collapsed down to a size only about 10 miles across. So it could fit in a city, basically, except for that if you brought one to your city, it would not be good. Because when you brought it to your city, it has the mass of the sun, which is 300,000 times the mass of the Earth. So you wouldn't really have brought the neutron star to Earth. It's really like you brought the Earth to the neutron star, because Earth is so small in mass, even though in size it's bigger, that the gravity of the neutron star would very quickly basically cause the entire Earth to disintegrate and form a layer about 1 centimeter thick on its
it's good
surface.
To know.
So yeah, don't bring one to town. Yeah. But because they're so massive and so compact, if you have 2 stars are, 1 million plus miles across, they can't be that close to each other because at minimum they're separated by their sizes. But now you take all that mass and collapse it down to only something 10 miles across, and they can be very, very close together without hitting, right? And that's why they're orbiting very, very fast and emitting all these gravitational waves in the process. And that's what caused the orbit to decay. And in that last moment, you have the boom, which was detected.
Now, when something implodes down to a black hole, or anything implodes like that, is it this down to the atomic level of the space in the atoms, like just squeezed all together?
So a neutron star is called a neutron star because it has been squeezed so much that its atoms can't exist anymore. The electrons all merge with the protons, and it is actually basically a ball of solid neutrons, which what most people don't realize is that, when you feel an object, a pen, anything, it feels solid to you. But it's actually mostly made out of empty space because the nucleus of an atom is 100,000 times smaller than the whole atom. So individual atoms are made almost entirely of empty space. All their mass is down in this very tiny nucleus way, way down in the middle. So when a neutron star forms, all that empty space is now filled, and it's all neutrons. And that's why it's so dense. If you had a teaspoonful of neutron star matter, it would contain as much mass as like an entire mountain does.
Amazing. Now, if, say, a black hole spit out matter or dissipated out some matter that was in it, would that matter expand back to normal size atoms?
Well, no, it can't do that because a black hole, by definition, is where the matter has basically been squeezed out of the universe, so to speak. It's got an event horizon, a place beyond which no information can ever come out again. So no. Now, in the case of the neutron star, when that explosion happens and some of the matter gets spewed out into space, neutrons by themselves are not stable particles. They will fall apart and become protons, and I think they must release an electron in the process. I'd have to look up the nuclear reaction there. But so they will, in a sense, the little bit that gets spewed out from that explosion will sort of become ordinary matter again.
I see. Now, can a black hole just keep growing and swallow galaxies? If not, then why?
Yes, a black hole will grow as long as more mass is falling into it. But that's the key. One of my favorite expressions that I like to remind people of is that black holes don't suck. They're not vacuum cleaners. They don't suck stuff in. The only way material gets into a black hole is if it falls in because it has an orbit that's crossing into the black hole's event horizon. So you have to have matter around that's falling into the black hole in order for it to gain mass. So what happens down, for example, in the center of a galaxy, where we know there's supermassive black holes at the centers of most galaxies, made famous in the movie Interstellar, where they went to visit one. And down in the center of the galaxy, there's lots of gas and lots of stars. So the black hole can feed on that because those things collide with each other, their orbits shift, and anytime an orbit shifts, it might cause the material to end up spiraling and falling into the black hole. When galaxies are young, there's a lot of that material around, and so the black holes are kind of eating a lot, and that makes them generate a lot of light coming from around them, from the material that's on its way in. And you may have heard of these objects we call quasars. Mm-hmm. And that's what a quasar is. It's basically the center of a galaxy where a black hole is eating a lot very rapidly. And we only see the most powerful quasars at very great distances, which means in the distant past when the universe was much younger. Why not around here? Because the black holes must still be in those galaxies even when they're much older. And the reason is because they've basically eaten up most of the material down in the center of the galaxy already. So there's not as much for them to eat anymore. So they don't shine so brightly like quasars anymore. But if you keep feeding them, they will keep growing in mass.
So if something has to fall in a black hole, which I assume is very small, how does it fall into it?
That's correct. A black hole is actually probably the most difficult thing in the universe to fall into by accident because it is so small. You're not just going to go run into one. But what happens is as material gets close to a black hole, for example, in the center of a galaxy, when a star comes fairly close to that supermassive black hole, just like the moon creates tidal forces on Earth that stretch Earth out. Well, a black hole being much more massive, it creates strong tidal forces, and it can actually rip stars apart as they get close to it. And then that gas from the star is now orbiting, and gas, because it's lots of individual molecules and they're colliding with each other, whenever there's a collision, one object loses energy and one gains energy. So you're going to have some objects that are going to lose energy and move closer to the black hole. And the end result is all that gas ends up forming a disk of material around the black hole. We call it an accretion disk. Right. And that matter, it's just going to keep basically spiraling in because the collisions are depriving it of energy. It's also very hot, so it's radiating energy away. That's why we can see these things with telescopes as quasars and other similar objects. But yeah, all that gas will spiral into the black hole. So you have this big disk of gas that's falling into the black hole because of that energy loss.
Now, how far can we see in our galaxy as far as light years? How far away can we see?
So in principle, we can see as far as we want in the observable universe. So the observable universe is, by definition, because the universe is about 14 billion years old, the farthest we can see in principle is 14 billion light years away. Because anything, if an object was 14 billion light years away, by which I mean its light took 14 billion years to reach us, and the universe is 14 billion years old, then when you see something that far away, you're seeing it at the moment of its birth. Right when the universe was born. There might be an object that's 15 billion light years away, but its light takes 15 billion years to reach us, which means we would now be seeing it as it was 15 billion years ago. But 15 billion years ago, the universe and it didn't exist yet. So there's nothing to see.
Wow. So that is amazing.
That's the farthest we can see is the observable universe.
So obviously we can see to a point where there isn't any black holes yet.
Not quite. It depends on how you look at that. We can see with our most powerful telescopes, some of the most the objects that we see at the greatest distances are some of these quasars. So these are places where there's a supermassive black hole already in the center of a galaxy. And we see them out almost to the, when the universe was just a few 100 million years old. Now with Hubble and with the coming James Webb telescope, we're hoping we might be able to see galaxies, if they were already in existence, even before the black holes existed. Now, there's a bit of a chicken and an egg question there. People aren't really sure whether the black holes came first and the galaxies formed around them, or the galaxies came first and the black holes formed in their middles. But we might be able to figure that out. But if you go back to far enough distances, you reach a time before stars existed. And then you're in a place where there's really not anything to see, with one exception, which is that the Big Bang itself should have generated an enormous amount of heat and light. And in principle, we should be able to detect that light left over from the Big Bang itself coming from that very edge of the universe. And we do. That is what's called the cosmic microwave background. It was first detected in 1960s.
Right, and that big horn thing. Right.
Right, with that big horn telescope. And now you see those beautiful pictures, maps that we make of the cosmic microwave background all across the sky. So we're actually looking at the universe as it was when that light was first released, which turns out, for reasons I won't go into right now, to be about 400,000 years after the Big Bang itself.
Now, is there any way possible that we could be wrong about the Big Bang?
It depends on what you mean by wrong.
Okay.
And this is kind of an important point. People have this this myth that gets spread that when you get a new theory in science, it means the old theory was wrong. And that's not true. And relativity is a great example here, because general relativity, Einstein's general theory of relativity, is a theory of gravity. That's why it explains things like black holes and so on. But we already had a theory of gravity for a couple hundred years before Einstein was even born. That was called Newton's theory of gravity. And Newton's theory of gravity works really, really well. You can land spacecraft on the moon with it. You can send a spacecraft past Pluto with it. You can explain most things in the universe with Newton's theory of gravity. So what's the difference? It turns out that there are some places where Newton's theory of gravity does not give you the right answer. For example, it does not predict gravitational waves. It doesn't give you the right answers for objects that are really, really strongly, super strong gravity, like neutron stars and black holes. But for most of the universe, it works great. So what general relativity did was it gave us a bigger view of gravity than we had with Newton. And it gives us a different interpretation of gravity, too. Newton had this idea of gravity as being kind of this magical force acting between two objects, whereas Einstein says, no, it's got to do with the curvature of space-time, and that's actually why you have to have gravitational waves when space-time changes its shape in order to propagate that information outward. So we have a different idea about gravity because of relativity, but Newton's theory was correct because you can't make all its successes go away. So now you come back to the Big Bang. Well, we see this leftover radiation from the Big Bang. We have all kinds of other experimental and observational data that fit with the Big Bang theory. All of that stuff, those are observed and experimental facts. You can't make them go away. It's always possible that in the future, we'll have some different theory that will give us a different interpretation of this. Perhaps even so different that we might not think of it the same way that we think of the Big Bang today, just like we don't think of gravity the same way Newton did. But you won't make all this evidence disappear. The evidence is there, and it's very, very solid.
Right. Now, do you think, along the relativity, do you think that it is possible, do you think it's totally impossible that something cannot go faster than the speed of light? And if so, what regulates that is as fast as anything can go?
So the idea that things can't go faster than light, that seems to be an indisputable and unget-aroundable fact. But there's a caveat there, right, which every science fiction fan is aware of. It says you can't go faster than the speed of light through space. So if you could somehow jump out of space into hyperspace, whatever that is, or take a shortcut through a wormhole, there might be ways around this. But that basic idea is fundamental in relativity, and it's one of the key thought experiments that I do in my book and in the talk that I think you watched, which is that what relativity tells us basically is that in our everyday, there's lots of ways to look at relativity, but one way to look at it is it tells us that in our everyday lives, we think space is one thing and time is another thing. Relativity tells us that's not right. They're actually merged together as this thing called space-time. And what that means is that because we think of them differently, we think, well, you can go as fast as you want by covering a certain distance in space in a short amount of time. But relativity says, no, it's all merged together in space-time, and the thing that's actually fixed is the speed of light. Different observers will disagree about the amount of space between two objects. They'll disagree about the amount of time between two events, but everyone will always agree on the speed of light. That's what relativity is built upon. That's its foundation. And that's an experimentally tested fact. In fact, every time you look at a telescope picture from the Hubble Space Telescope or so on, you're proving that fact. Because if the light from all those distant objects wasn't coming to us all at the same speed, we'd get a big blur instead of those nice clear images that we have. And so we know that no matter how fast all those objects out there are moving, their light always comes at the same speed, which is a kind of a weird idea. It's not the way we think of objects in everyday life. You know, if you're in a car and you have another car next to you, you'll say it's going some speed relative to you. But somebody on the ground will say, no, it's going a different speed. And somebody going the opposite direction will see it go by really fast, right? But with light, we all always see it go the same speed. And that sets up this very simple thought experiment that drives a lot of people crazy, right? But imagine I'm in a spaceship and I'm going any speed I want to go. I'm not going to put a limit on it. I'm not going to tell you I'm not going faster than the speed of light. I'm saying I'm going as fast as I want. Well, there's light coming from my face, right? Infrared light that I emit, or I could have headlights on my spaceship. And according to me, that light has to be going out ahead of me at the speed of light because everyone sees the speed of light. Well, what do you see if you're watching me? You also see the light going the speed of light because everyone always agrees with that. But you also see that light is going out ahead of me, which means I'm going slower than the speed of light. So there's nothing you can do to get around that. Any object you look at, it cannot outrace its own light. And therefore, it's always going slower than the speed of light.
So if you had a ship going near the speed of light with a headlight in front of it, it would catch up to its light in front of it?
No, it would not catch up to it because it also has to see its light going the speed of light. So you would always see the light going ahead of it. Now, if it was going, let's say that it's going 99% of the speed of light, you'd see the light going the full speed of light, and you'd see the ship going 99%. So the light would gradually be pulling away from it. But there's nothing it can do to actually catch its own light. There's no way that can happen.
Wow. Now, what about how come, or do you think it will ever be figured out, a theory of everything? I know I said that kind of a backwards question, but you get what I'm trying to say, right?
Yeah, well, so the history of physics has been a history of unifications, in a sense. You know, for example, the word universe actually was, I don't know exactly when it was first used, but it's basically what Newton discovered. Because before Newton, people thought that there were laws of nature that existed on Earth, and there were separate laws for the heavens. And Newton showed, nope, the same things that are keeping the moon in orbit of the Earth and the heavens is the same force that's holding us down to the ground. He showed that the same forces operate on Earth and in the heavens. And that's why we call it a universe now, because it's one thing, right? So that was kind of the first big unification, that we unified the laws of physics across the universe. Then later, as people did experiments in electricity and magnetism, people had known about electricity, known about magnetism, but in the 1800s, they figured out that electricity and magnetism were different manifestations of the same thing that we now call electromagnetism. So that was a unification. Einstein, in a sense, unified space and time as space-time. And as time has progressed, we've learned that there's four basic forces in nature: gravity, electromagnetism, the strong and weak nuclear forces. And scientists suspect that under very high energy conditions, like in the early universe, you would find that these are actually just different manifestations of a smaller number of forces. So the electromagnetic and weak forces were actually unified in a theory back in the 1980s, and that's been tested and verified with particle accelerators. The strong force, a lot of scientists think they have a handle on how the strong forces unifies with those other two. So if that's correct, then we're down to two forces in the universe: that grand unified force, as they call it, or gut force, kind of a weird name, and gravity. So the idea behind a theory of everything is that we would find a way to unify gravity with those other three also. And then we would have one theory that explains all forces and actions in the universe. So theory of everything is a theory of the everything of physics. It doesn't mean you're going to be able to predict everything that happens in the universe. It just means you'll understand the underlying science behind it.
I see. Now, there's someone sent me a link today of Jonathan Volkel, Unified Force. Have you ever heard of that?
It sounds vaguely familiar, but I can't say I know what it is.
Okay. I didn't really. I'm unfortunately I didn't get a chance to look at it. So I remember being like, I think I was in, I don't know, high school at some point, and the science teacher had us try to explain what time is, and I think we all failed. And this may be kind of a layman question here, but how do the thoughts of linear time work with relativity?
It's still there. And let me just back up one sec. If your viewers, listeners there haven't seen the movie Theory of Everything about Stephen Hawking, they should, because it's a very cool movie about him, but it also talks about what we mean by a theory of everything, much like I was trying to say very briefly there. Time. So what is time? Well, scientifically, it is very difficult to define time, but the simplest sort of normal definition we have from time is it's the direction in which entropy increases. Disorder increases. So it's the idea is, if you're familiar with this, what's called the second law of thermodynamics, the idea that disorder always increases, what they're talking about is, let's say you have a jar and you got some smelly substance in the jar and it's got a lid on it. Mm-hmm. If you take the lid off, well, those molecules, why were they in the jar? They were in the jar because that was as far as they had to move around, but they're always bouncing around randomly. If you take the lid off, you've now given them a lot more space to bounce around randomly in. So they will. Now, in principle, they could all at one moment decide to be back in the jar. But the probability, if you calculate that out, of it happening is it would never, ever happen. So the idea that the molecules will escape from the jar but won't spontaneously go back into it, that's the direction of time.
Oh, wow.
So that's the basic idea of time. It's the direction that things will flow on their own. Now, in relativity, it doesn't change that. What relativity tells us is that different people will different observers will measure the amount of time between two events differently.
Really? Wow.
But it's still a linear time.
Uh-huh. Well, like if you slip and fall on the ice or something like that, you can never go back that billionth of a second to take that step back.
That's right.
It's just
That's
forward
right.
moving. But that brings me to a question kind of out there a little bit. Do you think time travel could ever be a possibility? And if so, is it only one way?
Well, that's a really good question. Time travel is certainly possible into the future because we're doing it right now as we speak. But and you can, to some extent, you have some control over that in relativity. If you travel fast enough, your time will move at a different rate than the rate of people staying back on Earth. Whether you could actually travel backwards in time is a very difficult question because relativity doesn't say anything about that. In fact, because it tells you that space and time are all intertwined and we can move back and forth in space, it makes you wonder, why can't you do the same thing in time? And so people have been investigating that question. No one knows the answer to it. Stephen Hawking has a famous saying that he doesn't believe that time travel is possible because he wants to keep the world safe for historians.
I remember saying a joke as a kid, something along the lines like, time travel will never happen because we don't see anyone from the future. So I want to skip back to black holes just for one second, and then we'll go back into more of relativity. First of all, do all galaxies that we know of have a black hole in the center?
We think yes, although it's not 100% sure. But all the galaxies that we've looked at and been able to check, they do seem to have supermassive black holes in their centers. Now, there's a little caveat on that, which is there are a lot of things out there that are kind of like really tiny galaxies, and it's not clear whether they have black holes in their centers or not. But for big ordinary galaxies, Milky Way type galaxies, they all seem to have a supermassive black hole down in their centers. And it's thought that these actually play an important role in regulating the rate at which galaxies can form stars, because as they're eating this material and generating all this energy and spewing out this radiation, it has effects on the entire galaxy. And so there are some correlations that have been seen that pretty strongly indicate that somehow, we don't understand exactly how, but what's going on down in the middle by that black hole is affecting things out at great distances within the galaxy in terms of how many stars are being born, for example.
Now, could there ever be a possibility of like a rogue black hole wandering in space between galaxies?
Sure. There's a lot of, we don't know a lot about how many black holes there are and so on. There have been some people who've imagined that during the Big Bang there might have been lots of mini black holes that formed that would be out there just floating around in space today. And could there be one that's a supermassive black hole that didn't ever get a galaxy around it? That's unlikely because its gravity would have attracted gas that was nearby. And so over time, it presumably would have sort of grown a galaxy around it from collecting this gas. But there could be black holes wandering around. But again, it's not something that anybody has to ever worry about, because just like they're the hardest thing to fall into by accident, they're also the hardest thing to have come wandering by you by accident. And we know there's none anywhere close to us or any big one close to the Milky Way, because you would feel its gravitational effects from great distance.
Wow. And speaking of gravitational effects from great distance, I also heard you say that like when someone feels weightless, like in the International Space Station or something like that, they're on a free fall. Can you explain what that's about?
Yeah, the space station is orbiting Earth because of gravity. So there's plenty of gravity where the space station is, right? The moon is orbiting Earth because of gravity. There's plenty of gravity out at the moon's distance. There's gravity everywhere. So being weightless has nothing to do with gravity per se. It has to do with falling. So you're falling. Whenever you're falling, you're weightless. And the simple way to understand it is if you're standing on a scale, well, if you're on the ground, it'll show a weight, right? Now take the scale up onto a diving board and jump off and have somebody push the scale off with you at the same time. Well, you'll both be falling at the same rate. Galileo showed us that hundreds of years ago, that all objects fall at the same rate, right? And since the scale and you are falling at the same rate, it's not going to read anything anymore. So it'll read 0. So you're weightless.
Okay. So you're basically saying that the space station is falling toward Earth?
That's correct.
Wow. And
so here's the Earth. Okay. Here's the space station. Yeah. The space station's falling. It should come straight down and hit it. Why doesn't it?
The rotation.
Because it's also going 17,000 miles an hour.
Oh, yeah. Okay.
So that by the time it falls this far, look where it is.
Yeah.
It missed. If you remember the old Hitchhiker's Guide to the Galaxy books by Douglas Adams, he said, flying is easy. All you have to do is throw yourself at the ground and miss.
Wow.
That's what the space station's doing. It's going fast enough so that even though it's always falling towards the ground, it always misses because it's going so fast. And that's why it has to go fast to be in orbit. If you don't go that fast, you do fall back down and hit the ground.
So there's a certain miles per hour or kilometers per hour that an object has to go so it doesn't fall. Does that change on the different heights of orbit?
Yes, the orbital velocity is dependent on how high you are. Yes. So in low orbit, like the space station, it's 17,000 miles an hour. As you go higher up, it gets slower.
I see. Now, I know the moon, basically moves a very little bit, doesn't it? Or I know that.
But the moon's actually going around Earth at about 3,000 kilometers per hour, a lot slower than the space station, but that's the orbital velocity out where the moon is. And in fact, if you got to see the solar eclipse this summer, or heard about the
yeah.
solar eclipse this summer, you know the shadow goes racing across the United States. Why? That's the moon's orbital motion.
Wow. And by the way, you built an app for that, and I had that app on my iPhone.
The Totality app, and it is still works because we have the next 5 total solar eclipses built into it as well. So just download the Totality app. It's free, and you can plan your eclipse trip for one of the upcoming ones, including the one in 2024 that's also in the United States.
All right, great. So I have a question in the chat room, and someone wants to know if you believe information can propagate faster than the speed of light.
What we understand about information is that it cannot. Information is also got to be encoded in some form, either as light or as particles. So if it's particles, it's going to go slower than light, and if it's light, then it's going to go at the speed of light.
Wow, interesting. Wow. What about, I know we're getting way off topic here, but what about on quantum physics when a reaction can be, it doesn't matter the distance of the two, is it 2 atoms or 2 electrons?
Right, two subatomic particles can become entangled, and then when one changes, the other one undergoes the same change, no matter how far away it is, instantly. So that kind of sounds like it's violating relativity, but it's not, and it kind of goes back to your previous question. Relativity doesn't really say that nothing can happen faster than the speed of light. What it really says is no information can be propagated faster than the speed of light. So if you have a particle here and a particle on the moon, and this one undergoes a change on Earth, and this one undergoes the same exact change on the moon at the same exact time, you would think, didn't that violate relativity? Mm-hmm. But no information was transferred between them, because the only way you'll know that they both changed at the same time is by somebody on the moon saying, hey, mine just changed too. Mm-hmm. That information is going to propagate at the speed of light. So you cannot use this to actually transmit any information at a speed faster than the speed of light, and therefore it doesn't violate relativity.
Oh, wow. And that is such a mystery how that works. And I know there's people speculating, multiverses and all that. And what's your thoughts on all that?
Well, I'm not a fan of the multiverse, I'll say that. That doesn't mean I don't think it might exist. It means I'm not a fan of it if it does.
Okay.
Because the multiverse is, well, we just talked about how the universe got its name. One thing, right? One ring to rule them all, or whatever. One set of laws for everything. The multiverse basically says everything that could ever happen and every possibility exists in some sense. And that's just weird to me. I like a universe. I like a plot, right? I like. My wife always makes fun of me because when we go to movies, I like movies that have a plot with a beginning, middle, and end. I'm not big on these ones that, just seem to go nowhere. Mm-hmm. I like a universe the same way. So our universe makes sense, right? It's got laws. It has a beginning in the Big Bang. We can kind of predict somewhat into the future, although we don't know all the laws of physics, so we can't predict too far into the future, but we can get some ideas about what's going to happen in the future. If you open it up to a multiverse, you just opened a huge can of worms. It might be that that's the way it is, but since nobody knows yet, I'm rooting for the theories that don't have a multiverse.
Uh-huh. Okay. Now, I would consider that gravity must be the foundation of everything. I mean, everything is all about gravity. How everything, the dust particles of the planets and the stars all gathered together. I know that without any of the forces, we wouldn't be here. But would you consider like gravity the first force?
You can't really do it that way. Basically, gravity governs, of the 4 forces, gravity governs everything that happens on large scales. And the reason is because the 2 subatomic forces, strong and weak, they only act over distances the size of atomic nuclei. So we don't notice them in our daily lives. But everything that, the reason we have bodies and the reason we can breathe, the reason Earth is solid, that's all electromagnetism. It's the interactions between atoms which are based on charged particles, electrons and protons that make up the atoms. But the key there is there's electrons, which are negative, and protons, which are positive. So two atoms can have very strong effects on each other electromagnetically, but if you put an Earth amount of atoms together, overall, it's electrically neutral. So the electromagnetic force just cancels itself out on very big scales. So on very big scales, you're left with gravity. That's all there is. And that's why it dominates on large scales. But we wouldn't exist without those other forces.
Right, right. So in the chat room, someone wants to know your thoughts or possibly the solution to Fermi's paradox.
Well, Fermi's paradox is a question about why we don't have clear evidence of extraterrestrial civilizations yet. And if you watch my Beyond UFOs video online or read my Beyond UFOs book, you'll know that my personal favorite answer to Fermi's paradox is that basically the prime directive of Star Trek. There's a galactic civilization out there already, and they just haven't told us about themselves yet because they don't think we're ready.
Yeah, I could agree with that actually. So one more thing about gravity is, do you think gravity is a standard throughout the universe? The forces of gravity are standard?
That's a very good question. So one of the goes along with that. How do we know that the same laws of physics are operating out in the distant universe as they are here? And the way we know is by observing. So we can look at, for example, galaxies interacting at great, great distance in the universe. And those interactions are perfectly explained by the same theory of gravity that we use to explain why we're here on the ground. So it's not just a think, we have actual evidence that gravity operates the same way throughout the universe. In a similar way, when we look at the light from distant objects, we can look at a spectrum and see these spectral lines, and they tell us what objects are made of. We see the exact same chemical elements in the spectra of distant objects that we see here on Earth. That's how we know that the same chemistry applies throughout the universe.
Wow. In this recent collision of stars, I remember I read that briefly, but there was elements of platinum, gold, etc. And how is that detected? Is that through waves somehow? Or spectrum or
that's
something?
Detected through those spectral lines in the light. So every chemical element has a unique set of spectral lines, kind of like fingerprints. So when you study a spectrum, you can determine what the object that produced that spectrum is made of. And one of the big mysteries, and another reason this discovery announced today is so important, where did all the elements come from? Well, the universe began with hydrogen and helium, and that's it in terms of the elements. But then we know that in stars, through fusion, hydrogen fuses into helium, but toward the end of a star's life, helium can fuse into carbon and oxygen and so on. Most of the other elements that we see were produced inside stars by fusion. Now, there's some heavier elements, iron. Fusion can only take you up to iron. Beyond iron, some of those heavier elements we know are produced during supernova explosions themselves, but there were a set of elements, including silver, gold, platinum, that no one really had a really good idea of the origin of, except that some people had done the calculations and built models that said they should come from neutron star mergers. So what we've gotten today is confirmation of that. These neutron star mergers produce these elements that previously we weren't really sure where they came from. So, if you have a gold wedding ring like I do here, that was produced by a neutron star merger. It's kind of an amazing thought.
Wow, amazing it is. And so how does that gather while it's floating out in space? Is it, again, does it form a planet in a star and stuff like that, and then just get embedded?
Yep. So galaxies, I like to think of galaxies like our Milky Way galaxy as cosmic recycling plants. So when stars die, they explode and they spew out all this material. If they were just out floating around in space by themselves, that material would just fly out, never to be seen again, right? But because they're in a galaxy and the galaxy as a whole has very strong gravity, that material flies out for a while, but then it gets collected back and mixes in with the rest of the material that's still floating around in that galaxy. So the same thing with this neutron star merger. It blows out this gold, but it doesn't escape to the distant universe. It's contained within the galaxy by the galaxy's gravity. And over time, gravity in more localized regions will form new stars. They will collect the gas together, form new stars and planets. And so these later generations of stars and planets will have all the material that was spewed out from stars that died before they formed. So our solar system, for example, formed about 4.5 billion years ago. The universe is about 14 billion years old. So that means stars were living and dying and spewing out all these elements for almost 10 billion years before our solar system was even born. And that's how those elements got here.
Wow, amazing. So now I'd like to just a couple of questions about Einstein. If he was never born, do you think we'd eventually stumble on relativity or not?
Yes. When you ask this question of historians, what they'll usually tell you, remember, relativity he published in two parts: special relativity in 1905, general relativity in 1915. The difference being that special relativity does not deal with gravity and general relativity does. And special relativity, it turns out, even though Einstein discovered it and published it in 1905, if you even look at the name of the paper that he wrote on it, one of the things he realized is actually was already embedded in the equations of electromagnetism that Maxwell had discovered 40 years earlier. So in a way, we already had relativity, special relativity, before Einstein. It's just nobody realized it until Einstein did. And when you talk to historians of science, they'll say Einstein wasn't the only person who was on that track of going, oh, there's something here. And a lot of people think, in particular, a guy named Poincaré might well have published the very same theory within 6 months of Einstein, if Einstein hadn't gotten there first.
How about that?
Now, general relativity is a little different. In general relativity, Einstein kind of went out on a limb thinking, about how the universe might work. And so most historians of scientists think he was way ahead of everybody else. That said, there were things that we were learning that had hints of it already. So I would say certainly within probably 20 or 30 years after 1915, someone would have probably figured out general relativity. But he probably gave us a 20 to 30 year quicker head start than we would have had otherwise.
Now, what would you think if Einstein was born today with technology at his fingertips? Do you think he could have advanced even more into what he was discovering?
That's a really tough question. I think if you talk to a lot of people, they might think that it would have prevented him from ever realizing his genius because he would have been too busy playing video games or something.
Smartphone, yeah.
It's right. It's not clear whether this technology is actually helping us at this point.
How about that?
On many different levels, right? It certainly puts more information at our fingertips, but that information had to have been first found by someone else. And of course, one of the big problems with all that information is there's a lot of fake information out there too.
Right.
And but there's a question as to whether it's hindering our ability to progress and students' ability to really realize their full potential. We don't know yet. Maybe it'll prove to be helpful, maybe not. So it's a really tough question to think about.
Right. And do you think there'll be another Einstein, another superhuman, figure that comes along and discover? It's all about discovery, isn't it, when it comes to physics and things?
Yeah, but I think a lot of scientists and historians of science would probably argue that there have already been many other people like Einstein. There's geniuses throughout history. Einstein wasn't, like I said, others were on the trail of what he was doing. He wasn't a different type of person. He just had really good ways of thinking about things and made these discoveries, but other people have made great discoveries since that time too. I think the reason he's so famous, well, there's two parts to it. One is because he was dealing with space and time, and you can't get away from space and time, right? I mean, that's always going to seem bigger than the latest discovery in atomic physics. Doesn't mean that the discoveries weren't equal in their overall magnitude in terms of their importance to our understanding of nature, but the space and time that Einstein got is going to seem bigger, right? And the other was there was actually some luck involved in terms of the way the media handled it. They were, nobody heard of Einstein until after the solar eclipse of 1919, when one of his key predictions was verified, and it became front page news. And that was when all of a sudden everyone heard of Einstein. So he was at the right time in the right place for a media moment.
That was the curvature?
Yes, yeah. The bending of starlight during a total solar eclipse, which was measured again during this recent one.
Oh, and by the way, did you go somewhere where you must have gone somewhere where you could see the total eclipse?
Yeah, I was up in Idaho Falls on the path of totality, yep.
Oh, wow, yeah. Yeah, up in Maine here, we didn't have too much of a...
No, you got to travel for the next one.
That's right. That's right. Well, this has been a real pleasure, as always, Jeffrey. I've always enjoyed talking to you.
Thank you very much. It's been a lot of fun.
And as I said, we'll have to have you back on to talk about climate change. That should be
Sounds great.
Thank you very much.
Sounds great. Thank you.
All right. You take care.
You too.
All right. Okay, everyone. So that's it for the show this evening. I thank you so much for tuning in. And we'll be back. I think it's next week. Yes, I believe it's next week. And our guest is the noted author, and I'm just Brad Steiger. And he has just published I think he's in his 80s now. So a real cool guy. I don't know how many books he's published, but I've been trying to get him on the show for quite a while, and I lucked out. He finally said yes. So Brad Steiger will be on next week. So thanks, everyone, and we'll be back next week. And on some Mondays, not every single Monday, but when we do have a show, it will be on Monday evening. Thanks a lot.